Hello, my name is Dr. C. Suresh Kumar, working as lecturer in mathematics at TRR Government Degree College, Kandapur. In this session, we learn about the topic, namely properties of vector spaces. First of all, we learn about the definition of vector space. Let F plus be a field. Here we take F is a field. There are two binary operations involved in a field. One is addition plus and other is multiplication dot. If a non-empty set V satisfies the following properties, namely three properties, then V is said to be a vector space over the field F. The first property is V plus is an abelian group with respect to vector addition. Here we are taking vector addition as a binary operation, and it is also called internal composition. We all know what is abelian group. In the definition of abelian group, we mention 5 laws involved in abelian group. They are: one is a closure law, second one is associative law, third one is identity law, fourth inverse law, fifth commutative law. First one, closure law. If we take two elements, alpha, beta in V, and we use the composition, that is a vector addition, the resultant alpha plus beta is also in V. So then V is said to be, V is closed with respect to vector addition. And second law, associative law. If we take three elements, that is, they are alpha, beta, gamma in V, if we take three elements in V, alpha, beta, gamma, alpha plus beta plus gamma equal to alpha plus beta plus gamma, then V is said to be associative with respect to vector addition. And the third law is identity law. That is, in V there exists an identity element, that is called identity law. For each alpha belongs to V, for each alpha belongs to V, there exists 0 bar belongs to V such that alpha plus 0 bar, that is equal to 0 bar plus alpha equal to alpha. Here 0 bar is called identity element in V with respect to vector addition. This is called identity law. And the fourth one is inverse law. That is, for each element in V, there exists its inverse element in V. For each alpha belongs to V, there exists minus alpha belongs to V such that alpha plus minus alpha equal to minus alpha plus alpha equal to 0 bar. Here already we will learn what is 0 bar. 0 bar is the identity element in V. Then minus alpha is called inverse element of alpha in V. This is called inverse law. And the fifth one is commutative law. That is, if you take any two elements in a the set V, alpha plus beta is equal to beta plus alpha. This is called commutative property. Then V is commutative with respect to vector addition. From these 5 laws, they are closure law, associative law, identity law, inverse law, commutative law. Then we called V plus is an abelian group under vector addition. Let us now move to the second property, that is namely called external composition, that is scalar multiplication. For each A belongs to F and alpha belongs to V, we have A alpha belongs to V. This is called scalar multiplication property. And the third one is law involved two types of properties. One is vector addition and scalar multiplication. They are divided into 4 separate laws. One is for every A belongs to F, and alpha beta belongs to V, then A into alpha plus beta is equal to A alpha plus A beta. This is first property. And second one is for every A comma B belongs to F and alpha belongs to V, A plus B into alpha is equal to A alpha plus B alpha. And the third property, for each A belongs to F and B belongs to F, alpha belongs to V, A into B alpha is equal to AB into alpha. And the fourth property is one belongs to F, alpha belongs to V, then 1 into alpha equal to alpha. Here one is called unity element of F. With these 3 properties, Roman letter number 1, 2, 3, we call V is a vector space over a field F. If V is a vector space over a field F, then it is denoted by VF. Okay. Let us take some examples. Let C plus dot R plus dot be the fields of complex numbers and real numbers respectively. Here we take C plus dot is the field of complex numbers, R plus dot is the field of real numbers. Then we mention 3 types of vector space formed. One is C is a vector space. C is a vector space over C, and R is a vector space over R, and the third one is C is a vector space over R. These are 3 examples for vector space 1, 2, 3. CC, RR, CR. Here C is a set of complex numbers and R is a set of real numbers. Next, the elements of V are called vectors and the elements of F are called scalars. If we take field F equal to real number system R, then the vector space VR is called real vector space. If we take field F equal to C, complex number system, then the vector space VC is called a complex vector space. In a vector space, there are two types of zero elements come into operation. One is the zero vector, that is belongs to V, and the other is a zero scalar, that is belongs to F. That's next theorem. If vector VF is a vector space and 0, 0 bar be the 0 scalar and 0 vector respectively, then we have to prove that 7 properties. One is A into 0 equal to 0 bar, 0 into alpha equal to 0 bar, A into minus alpha equal to minus A alpha, minus A into alpha equal to minus A alpha equal to 0 bar implies A equal to 0 bar or A equal to 0 or alpha equal to 0 bar, and the sixth one A into alpha minus beta equal to A alpha minus A beta, and the seventh one minus A into minus alpha equal to A alpha. For that proof, first one, A into 0 A into 0 bar equal to A into 0 bar plus 0 bar, right? And by using distributive law, this is A0 bar plus A0 bar. Here we write A0 bar plus 0 bar on left side. From this equation, from left cancellation law, we get 0 bar equal to A into 0 bar. This is proof for first one. And the second one, 0 into alpha equal to 0 plus 0 into alpha, that equal to 0 alpha plus 0 alpha by distributive law. So 0 plus 0 alpha, right? We are adding 0 bar, 0 vector on left side. From this equation, by right cancellation law, we get 0 bar equal to 0 alpha, right? And the third one is, third proof, A into minus alpha, A into minus alpha equal to minus alpha. From this, we are taking A into alpha plus minus alpha equal to A alpha plus A minus alpha. Okay. This is A into 0 bar, A into 0 bar. So from 1 we learn A into 0 bar equal to 0, 0. So A alpha plus A minus alpha equal to 0 bar. So from this, A minus alpha is the additive inverse of A alpha equal to minus A alpha. A minus alpha is the additive inverse of A alpha. Okay, this is proof of 3. Next, proof for 4, minus A into alpha. Now, A plus minus A into alpha. This is called 0 alpha equal to 0 alpha equal to A plus minus A into alpha equal to A alpha minus A into alpha by distributive law. We know 0 alpha equal to 0 bar, that is A alpha plus minus A alpha equal to 0 bar. So minus A alpha is the additive inverse of A alpha. So minus A alpha equal to minus A alpha. This is proof for 4. And the fifth one is, if A alpha equal to 0 bar, and what is our proof? We have to prove either A equal to 0 or alpha equal to 0 bar. If A equal to 0, there is nothing to prove. Assume that A not equal to 0. Then, since A not equal to 0 and this element belongs to field F, from the field definition conditions, we have every non-zero element of a field has multiplicative inverse. Hence, here in particular the element A also has multiplicative inverse. Let it be A inverse, then there exists A inverse belongs to F such that A into A inverse equal to A inverse into A equal to 1. Okay, this is the definition for field. What is field? Every non-zero element must have multiplicative inverse. Again, A alpha equal to 0 bar. If we take multiply with A inverse on both sides, A inverse on both sides, we get A inverse into A alpha, that is 0 bar, so A inverse into A equal to 1, 1 into alpha 0 bar, one into alpha equal to alpha 0 bar. So if A equal to 0, there is nothing to prove. If A not equal to 0, we prove alpha equal to 0 bar. And the next one is sixth one, A into alpha minus beta equal to, we write A into alpha plus minus beta by distributive law, A alpha plus A into minus beta. That is A alpha minus A beta we get. So this is proof for sixth one. And the seventh one is minus A into minus alpha equal to, we are using either 3 or 4, whatever may be for this. This is minus of A into minus alpha equal to minus of minus A alpha equal to A alpha. This is the proof for seventh one. These are all the characteristics of a vector space. and we complete the theorem of 1. And the second theorem, namely, let Vf be a vector space if A comma B belongs to F and alpha belongs to V, where alpha not equal to 0, then A alpha equal to B alpha implies A equal to B. And the second one is, if A belongs to F where A not equal to 0 and alpha beta belongs to V, then A alpha equal to A beta implies alpha equal to beta. For this proof, we take the first one, A alpha equal to B alpha. So A alpha minus B alpha equal to 0 bar. If we common alpha A minus B into alpha equal to 0 bar. Either A minus B equal to 0 or alpha equal to 0. A minus B equal to 0 or alpha equal to 0. Since by giving data alpha not equal to 0, hence A minus B equal to 0, that is A equal to B. And the second one, A alpha equal to A beta, then A alpha minus A beta equal to 0 bar. If we common A into alpha minus beta equal to 0 bar. From this we write either A equal to 0 or alpha minus beta equal to 0 bar. A equal to 0 or alpha minus beta equal to 0 bar. By given data, since A not equal to 0, we have alpha minus beta equal to 0 bar, hence alpha minus beta equal to 0 bar, that is alpha equal to beta. These two theorems belongs to the properties and the characteristics of a vector space. So in this class, first of all we learn about what is a vector space. There are three properties: vector addition, scalar multiplication, and both of them. Then V is a vector space and it is denoted by Vf. Vf represents what? V is a vector space over the field F. And next, examples, three more examples we have to learn, that is CC, RR and CR, and some of the primary notes. There are two types of vector spaces. One is real vector space and another is a complex vector space. Real vector space and complex vector space. And the elements of V are called vectors, and the elements of field F are called scalars. And there are two types of zeros elements involved in the vector space. One is 0 bar and 0. 0 bar is the zero vector belongs to vector space V, and other is a zero scalar that belongs to field F. And we learn two more theorems, and this is the first one, and this is second theorem. So this is a line about properties of vector space. I think students must be benefited from this class. Thank you, one and all.